Hey everybody, welcome. In this channel, we're going to be going over Chapter 2, Biology 1406, Chapter 2, and this chapter is about chemistry. You may be wondering, before we start, let me just take a side note. You may be wondering why we're covering Chapter 2, which covers chemistry in a biology class, and the answer to that is pretty straightforward. Biology 1406 is essentially a cell biology class. It's a cell and molecular biology class. We're going to be spending most of the semester talking about the cell and the components of the cell and how that works. The reason for that is because cells make up life, right? And a cell is the basic unit of life. You can't be simpler than a cell and usually be considered life. So, because all life forms are based on cells, and the cell is the basic unit of life, it makes sense to understand how a cell works. That way, when you move on to other biology classes and you're talking about groups of cells, and tissues, and organs, you have a basis. All life is based on that knowledge. Also, if you went into microbiology and you studied how bacteria works, those are also cells. So here's the thing. You can't understand how cells work unless you understand how the proteins and the molecules and all of the ions inside of the cells work. And those are based on molecules. Those are based on molecular interactions. When one protein interacts with another protein, that's a molecular interaction. When an enzyme breaks down a substrate, that's a molecular interaction. When macromolecules are formed, all of those are molecular interactions. So what you need to understand is if you don't understand chemistry, you won't understand molecular interactions. And you really won't understand what's going on inside of the cell, which means you fundamentally won't understand biology. So Chapter 2 covers chemistry, and so we need to do a very, very basic overview of this chemistry. So let's start with chemistry. Chemistry is the study of matter, right? Matter is anything that takes up space. Anything that takes up space and has mass is matter. And that is based on the elements. Have you ever seen the periodic table of elements? You got hydrogen, helium, lithium, and so on. Well, those are the elements that make up matter. Okay? And organisms like you and me and all the other life forms are no exception. They are made up of elements. And those elements, one unit of an element is called an atom. So you can have an atom of carbon, an atom of helium, an atom of hydrogen, right? One unit of an element is called an atom. But if you recall, atoms can form bonds with one another. And when they bond to one another, that's called a molecule. So a molecule is simply atoms which have bonded molecularly with one another. Atomic bonds form molecules. Okay, so what do these atoms look like? Atoms are comprised of three subatomic particles. You've got positively charged particles called the protons. You've got particles that have no charge. Those are called the neutrons. And you've got particles that have a negative charge, and those are called the electrons. Okay, so you've got protons, neutrons, and electrons, and those are called subatomic particles. Those subatomic particles make up the atoms, make up the elements. Okay, and what you need to realize about this is something interesting. The protons and the neutrons, you see how they're hanging out near the center of the atom? Okay, they hang out in an area called the atomic nucleus. Protons and neutrons exist in the atomic nucleus, usually somewhere near the center of the atom. Okay, and look how big they are. Protons and neutrons are quite big compared to the electrons. See how small they drew the electrons here? In fact, they didn't do this justice. In fact, they should have drawn it a lot different. Protons and neutrons are roughly the same mass, okay? They are roughly the same size. Protons and neutrons are roughly the same size, and they call that mass the Dalton, okay? They are 1 Dalton big in mass. Electrons, on the other hand, you see these little electrons? Well, they are 1/2000th the mass of a proton or a neutron. So they are tiny. And because they're so tiny, a lot of times you don't even factor the mass of an electron into your calculations. They're so negligible. Okay. So anyway, a proton and a neutron, protons have positive charge, neutrons have neutral charge. They exist in the atomic nucleus. They are 1 Dalton big each, and they exist in the atomic nucleus. They are 2,000 times more massive than the electrons, which, by the way, the electrons are not in the atomic nucleus. Electrons actually exist in these 3-dimensional areas as kind of a cloud. These 3-dimensional areas are called orbitals, okay? Electrons exist in 3-dimensional zones or areas around the atomic nucleus, and these are called orbitals. And you can have multiple of these 3-dimensional areas. But here's the interesting thing. We'll get to this in a little bit, but just as a foreshadowing, each 3-dimensional area or orbital can house up to 2 electrons. Okay, just try to remember that. Each 3-dimensional space around the atomic nucleus, called an orbital, each orbital can have as much as 2 electrons in it. And then once you've filled that orbital, you have a different orbital with a different shape, a different 3-dimensional footprint, and that can house another 2 electrons. Okay, so again, this slide summarizes what I just said. You got the atomic nucleus, which consists of neutrons and protons. Those are 1 Dalton big, whereas the electrons are 1/2000th the mass of a proton or a neutron. Okay. Here's this meme I like. Atoms consist of 99.999% empty space. What does that mean? Where did this meme come from? So let me explain this. This is actually really interesting. Remember I said the atomic nucleus has the protons and the neutrons, and those are quite big compared to the electrons. Well, here's what you need to understand. Let me see if I can find a little pencil eraser. Okay. Let me show you something here. I've got here, I don't have a pencil eraser, but I have a little eraser tip here. You see, this little bit of eraser, okay? Imagine if I took this little bit of eraser and popped it off, okay? It would just be this tiny little nub of eraser. If I were to put this little nub of eraser in the middle of Cowboy Stadium, in the middle of a football field at the 50-yard line, this mass, this little eraser would represent the atomic nucleus, you know, with the protons and the neutrons of an atom, okay? And remember I said the electrons are 1/2000th the size of that. So let me actually draw this. Check this out. This is actually really fascinating. So imagine you've got this tiny little dot that you can't even barely see, and that's your atomic nucleus, the protons and the neutrons. And then you were sitting in the middle of Cowboy Stadium, right? You know, somewhere at the 50-yard line, okay? And you've got this little pencil eraser in the middle of this football field. Well, the electrons that I said are 1/2000th the size of the pencil eraser, so you couldn't even see them, because if they're 2,000 times smaller than this little pencil eraser, you're not seeing the electrons, right? The electrons would be buzzing around in various orbitals, in a bunch of orbitals, the rest of the football field, Okay, that's what an atom would look like. If you could zoom into an atom and look at it, the protons and the neutrons would be this tiny little speck at the center of a giant football field that you can't even see the football field because the electrons are in their various three-dimensional spaces around the football field, right? So what is an atom then? If you think about it that way, can you see the football field? Can you see the football field? No. So what is an atom? An atom is basically empty space, isn't it? It's just a ton of empty space with a little pencil eraser of protons and neutrons in the middle. So because of that, physicists have learned that atoms and matter, for that matter, no pun intended, is mainly empty space. Okay, the protons and the neutrons, even though they're 2,000 times bigger than the electrons are tiny and they're taking up massive amounts of space. So if you think about that, atoms are mainly empty space. You're mainly empty space. I'm mainly empty space. This is why things like X-rays can travel right through my body out the other side without ever hitting anything, because we're mainly empty space. So that's why you'll see memes like this pop up. Atoms consist of 99.999% empty space. That means the computer you're looking at, the chair you're sitting on, you yourself are mostly not there. It's pretty interesting stuff, you know. Matter, even though this table seems solid, right? This table seems super strong and solid. It's mainly empty space. And when two different hands come together, bam, it seems like they're both solid, but that's just repelling forces between the atoms that hit, you know. Otherwise, it's mainly empty space. Okay, good to understand. Very good to understand. So let's move on. Now we know that you've got subatomic particles, you've got protons, neutrons, and electrons. Now, let me show you what you're going to see on the periodic table of elements that demonstrates or exhibits all of the different elements. On the periodic table, you'll see these symbols, okay? These are called chemical symbols. And notice this. This is C for the element carbon, okay? And then you'll see a smaller number up to the top usually, and a larger number near the bottom, okay, of the chemical symbol on the periodic table of elements, right? So this number at the top, the smaller number, is called the atomic number. And what you need to know about the atomic number is that the atomic number is the number of protons in the element, okay, or the atom. So carbon has 6 protons. This bigger number at the bottom, this is called the mass number, okay? And what that is that it's the sum. You know what sum means, right? Addition. It's the sum of protons and neutrons in the atom, okay? So if carbon has 6 protons, well, how many neutrons would it have? If its mass number, which is the sum of the protons and neutrons, is 12. Well, what's 12 minus 6? 6. So carbon has 6 protons and carbon has 6 neutrons. Why? Because 12 minus 6 is 6. All right. So what's cool about the periodic table of elements is that if you look at an element, you can quickly tell how many protons it has. You can quickly tell how many neutrons it has. And let me tell you this symbol will also tell you how many electrons an atom has as well. Let me explain this because it can be a little bit confusing. To understand how you would figure that out, to understand that, you need to remember one thing, and you need to write this down. You need to remember this. Elements, or I should say atoms. You write down atoms. Atoms, by definition, have the same number of protons as electrons. You know why? Because the word atom, the term atom, means uncharged element or uncharged particle. Okay, atoms are uncharged. If someone says I have an atom of carbon, they're not giving you a charged form of carbon. They're giving you an uncharged form of carbon. Okay, if someone were to give you a charged form of carbon, they can't say I'm giving you an atom of carbon. Now they have to call it an ion. I-O-N. Okay. So just understand, if you see a little plus sign next to an element or a little minus sign next to an element, you don't call that an atom. That's inappropriate. Do you see a little plus sign or minus sign next to this carbon? No, there's no plus 1 or plus 2 or plus 3. There's no minus 1, minus 2, minus 3. So if you look at the periodic table of elements, when you look at that table, all of those elements that they've put on that table are atoms. They are all uncharged. So what does that mean? What if I were to ask you, how many electrons does carbon have? Well, if I'm talking about carbon atom, the uncharged form of carbon, for every plus charge, proton, you need a minus charge, electron, right? And how many plus charges do you have? 6 protons, 6 plus charges. How many minus charges would you have in the atom? 6 minus charges, 6 electrons, okay? So here's the cool thing. Again, on the periodic table of elements, just by looking at a symbol, just by glancing at a symbol, I can tell you it has 6 protons, 6 electrons, and 12 minus 6 is 6 neutrons as well, okay? That is how you interpret a chemical symbol. That's the difference between an atomic number and a mass number. And there you go. Now, sometimes you'll see this. Look at this here. Look at this here. Look at carbon. This guy on the right is called carbon 13. This guy on the left is called carbon 12. I think you can see why. Because the mass number here on the right is 13. Mass number on the left is 12. What's going on there? Well, how many neutrons does this carbon on the left have? It has 6, right? 12 minus 6. How many neutrons does this carbon on the right have? 13 minus 6. So it has 7 neutrons. So what does that mean? These are called isotopes. If you've ever heard the term isotope, that means a element with a different number of neutrons. So if you have different number of neutrons but the same element, then it's called an isotope. And sometimes you can have an isotope that results in a radioactive state. So for example, there's a carbon called carbon 14. You see here at the bottom, instead of 13, it'll say 14. How many protons does it have? 6. How many electrons? 6. But because it's carbon 14, it would have 14 minus 6, or 8. It would have 8 neutrons, right? 8 neutrons. So carbon 14 is actually an isotope of carbon, isn't it? And here's the thing. Carbon 14 is radioactive. It's radioactive. Because of this weird ratio of neutrons and protons, it causes a very unstable atomic nucleus. Okay, remember the atomic nucleus where the protons and the neutrons exist together as a little pencil eraser? Okay, well, when you have an abnormal number of neutrons and protons, this can cause the protons to... I always explain it like this. The protons are positively charged. They really don't want to see each other. They don't want to come into contact. That's my best way as a biologist of explaining what's going on. So you've got this weird ratio of neutrons and protons. And because of that, you got these positive charges that are kind of getting too close for comfort. And that causes, the nucleus to become unstable. The nucleus kind of is not happy with the situation. And because of that, it's fluxing, right? There's a lot of commotion going on in the atomic nucleus. That, uneasiness is releasing a bunch of energy, and that's radioactive energy. That's radioactive emissions. That's what radioactivity is. It's the essentially the atomic nucleus not being happy because of a weird ratio of neutrons and protons, and it trying to destroy itself, right? The atomic nucleus is trying to destroy itself because those protons want to get away from one another, right? Does that make sense? And eventually, the atomic nucleus does destroy itself, and that's called the half-life. Have you ever heard of half-life? I'm not talking about the video game. The half-life of a isotope. Radioactive isotopes all have half-lives. They all destroy themselves eventually, and they break down into other elements, completely different elements. So anyway, that's not the topic of this chapter, but just so you know, that's what radioactivity is, okay? And it's releasing a bunch of energy, and that energy can hurt your cells, hurt your DNA, hurt your molecules inside of your body. Okay, so now you know what an isotope is. The one on the left here, this is carbon-12. This is the most common form of carbon. This is the carbon that you will see on the periodic table of elements, right? This is the one you see on the periodic table of elements. The other forms like carbon-13 and the radioactive one I just told you about, carbon-14, those ones, they're less common, and they actually aren't on the periodic table of elements, but you should know that they exist. So here's the thing. What happens when you have a different number? What happens when carbon has a different number of neutrons? See? Well, then it's called an isotope, right? What happens when carbon has a different number of electrons? Electrons. So let's say carbon, instead of having 6 electrons, what if it had 5 electrons? What do you think would happen there? Well, in that case, carbon would have one more proton than it has electrons, so it would have a charge, right? It would have a charge. What would its charge be? If it had 6 protons, 6 plus charges, and only 5 electrons, 5 negative charges. So you'd have 6 plus charges minus 5 negative charges, you'd have a plus charge, right? So if you ever saw C with a plus next to it, which you really don't see all that often, if you saw a plus sign, a 1 plus, that just means you have 1 extra proton, okay? And if you ever see a minus here next to an atom, you can't call it an atom anymore. You have to call it an ion, and that means you have 1 extra electron. So if you had 7 electrons and you had a minus here, that's what it is. You have 1 extra electron. If you have 5 electrons, you'd see a plus here. If you had 4 electrons, you'd see a 2 plus here. That's kind of how it works. And remember, when you see pluses or minuses next to an atom, you don't call it an atom anymore. It's no longer an atom. It's called an ion. When you see charged atoms, don't call it an atom. Call it an ion. Okay? Now, here's the thing. Here's the thing you need to understand. So you can have weird numbers of neutrons and still have carbon. You can still have weird numbers of electrons and still have carbon. But can you have weird numbers of protons and still have carbon? Think about that for a second. You know how carbon has 6 protons? What if I had 5 protons? Am I still carbon? The answer is no, okay? You can have weird numbers of neutrons and still be carbon. That's just called an isotope. You can have weird numbers of electrons and still be carbon. That means you're an ion. But you can't have weird numbers of protons and still be carbon. Here's why. By definition, okay, you guys need to understand this. By definition, if you have 6 protons, you are carbon. Okay, by definition, if you have 6 protons, you are carbon. So for example, if I walked up to you one day and I said, okay, hold out your hands, close your eyes, I'm going to give you an atom. You'll never guess what it is, but it has 6 protons. You could just laugh and say, you gave me carbon. Because by definition, carbon has 6 protons. You cannot have 6 protons as an atom and not be carbon, okay? So what's the most important subatomic particle for identifying a element? The protons. Cool. All of that is summarized on this slide. Notice again what I said at the bottom. Unless indicated, an atom is neutral in charge. So neutral means atom. Anything plus charge, minus charge is no longer, don't call it an atom. Call it an ion. That means charged. Okay, so this is the periodic table of elements. And we're going to be talking about the periodic table of elements. Look at this. You've got rows, okay, rows called periods, and then you've got groups, which are the columns. Okay, so we're going to be talking about the periodic table of elements, and you'll understand why we have rows and we have columns. But at first, my throat's getting kind of dry. I've been talking a long time, so I'm going to take a little break. All right, you guys can take a little break too. Stretch your legs, relax. Maybe get some coffee, and I'll be back in just a second. Break time. Hey everyone, welcome back from break time. Hopefully you had a nice break. Let's get back to it. So where we left off, we were talking about the periodic table of elements, and I was about to go into what the periodic table is showing. So what you see here on the periodic table of elements, you see the different elements, right? You've got hydrogen at the top left, you've got helium to the top right, and then you can go to the next row, lithium, beryllium, boron, etc., etc. So why is the periodic table arranged how it is? What you need to know when you're reading the periodic table of elements, you're basically reading it like a book. The first word is hydrogen. The second is helium. Then you go down to lithium. Okay, so you're reading it like a book. What I mean by top left, you start at the top left, you read to the right, then you go to the next row, you read to the right, you go to the next row, you read to the right. So what's increasing as you're going from element to element? Well, the first element, hydrogen, at the top left. The reason hydrogen is at the top left is because of its atomic number. Atomic number. Remember the number of protons. So if hydrogen has a 1, you see this number at the top of hydrogen is 1. How many protons does hydrogen have? 1. Hydrogen has 1 proton, which means helium, which has a 2 up here, has how many protons? 2. And then we go to the next row. How many protons would lithium have? What's its atomic number? 3. And then so on and so forth. You've got 4, 5, 6, 7, 8. So for example, oxygen has 8 protons. Fluorine has 9 protons. Neon has 10 protons. So that's essentially it. Do you remember what I said about atomic number? If you have, for example, remember carbon? How many protons did carbon have? We just talked about it. Carbon has 6 protons. Notice how it takes up the 6th slot on the periodic table of elements. Carbon has 6 protons. Therefore, here is carbon right here with a 6 as its atomic number. Can you have 5 protons and be carbon? Nope, that's boron. You see what I'm saying? If you have 6 protons, you are carbon. And the periodic table is showing you in order, left to right, up to down, of all the different elements and their atomic numbers. So you have all the different elements and their respective atomic numbers. So the heaviest of elements over here at the bottom right, it appears this guy has 118. I'm not even going to try to pronounce him. 118 protons, okay, would be the heaviest and the most massive atom, okay? So the least massive atom, the lightest atom, would be hydrogen, okay? And how many electrons does hydrogen atom have? If it has 1 proton, it has to have 1 electron. How many electrons does helium have? If it has 2 protons, because its atomic number is 2, but it's a, do you remember what it is? It's a atom, right? Which means uncharged. All of these are atoms. They are uncharged. So there you go. There's your cheat sheet right there. whatever its atomic number is not just the number of protons, it is the number of electrons if you're talking about the uncharged atom, okay? The periodic table is uncharged atoms. So the number of protons is the number of electrons, okay? So hydrogen has 1 proton, it has 1 electron. Helium has 2 protons and 2 electrons. Lithium has 3 protons, it has 3 electrons. Okay. What about neutrons? Okay, let me take a look here. Do you remember I said the mass number on the bottom is the number of protons plus the number of neutrons? Here's something very interesting that you should understand. Look at this. This is weird, right? Look at this. Hydrogen, what's its atomic mass? What's its atomic mass? 1. So it has how many protons? 1. What's its mass number at the bottom? I know it's hard to see, but you can look at your PDF handouts if it's hard to see on this. It's also 1. What does that mean? If its mass number and its atomic number are both 1, how many neutrons does hydrogen have? 1 minus 1 is a big 0, right? So, you know what that means? Hydrogen has 1 proton, 1 electron, and that's it. Isn't that weird? You might think, oh, don't all elements have neutrons? Nope. Hydrogen does not have a neutron. So what is a hydrogen? This is actually, I'm stressing this because it's actually really important, especially when we start talking about pH. You're going to really need to understand this. A hydrogen does not have a neutron. So what is a hydrogen atom? What is a hydrogen atom? It is a proton with an electron. That's all hydrogen atom is. It's a proton hanging out with an electron. Okay? That's hydrogen. So please remember that hydrogen is nothing more than a proton hanging out with an electron. Okay? And let me actually tell you this now. You know, normally I don't mention this till later in the semester, but maybe you can handle this. Think about it. If hydrogen, let me show you something. This is really actually important to understand. Actually, this will help you understand pH. It will help you understand proton gradients. It will help you understand cellular respiration. It will help you understand photosynthesis. This will help you understand a lot of things. So please pay attention to this. It's not that hard to understand. It's actually really handy to know. So hydrogen, H, what does that equal? What does that mean? Hydrogen has an atomic number of 1. So how many protons does it have? It has 1 proton. And it's an atom. So if you have 1 proton, how many electrons do you have? 1 electron, just 1 electron. And its mass number is also just 1. So how many neutrons? No neutrons. So again, what is hydrogen? Hydrogen is a proton with an electron. Okay, that's what hydrogen is. Now, do you remember, that's hydrogen atom, right? Hydrogen atom is a proton hanging out with an electron. This is really important. What happens if its electron goes away? What if I steal its electron, take it away? That can happen. I could steal its electron. Is it still called hydrogen atom? No, because now you have a plus charge proton and nothing to balance it out and make it neutral, right? You know, you realize what I'm saying? So now what would you call it? Would you call it an atom anymore? No. Okay. It's now called H plus, also known as hydrogen ion. Okay? Hydrogen ion. So when someone says hydrogen ion, H plus, they mean proton. These are synonyms. They are the exact same thing. Okay, so this will help you a lot when you're talking about protons and you're talking about proton concentrations or hydrogen ion concentrations. You're talking about pH. If you remember this simple little trick and this simple fact, a lot of things are going to make a lot of sense. More advanced things are going to make a lot of sense. Okay, so that's good to understand. So let's keep going. Look at helium here at the top right of the periodic table. You see helium? Helium? Okay. Helium has an atomic number of 2. So how many protons does it have? 2. How many electrons does it have? 2. And its mass number, the little number below it, that number is 4. Okay, its mass number is 4. So how many neutrons does helium have? Well, it looks like 4 minus 2 is 2. So helium has 2 protons, 2 electrons, and it also has neutrons. It has 2 neutrons as well. Does that make sense? So you can figure out what's going on. Now you understand how protons factor in, how to figure out number of protons, how to figure out number of electrons, how to figure out number of neutrons. And you figured out that you read the periodic table from the top left to the bottom right, and what you have is increasing number of protons, right? Increasing atomic number. That's great. But what we haven't discussed is what are these rows, you see? Why is hydrogen way at the top left, helium way at the top right, and then why do you skip to lithium at the on the second row on the left? Why is hydrogen way over here, helium way over here, and why do we have different rows, and why are the rows arranged like this? Okay, so that's actually the next topic of discussion, and that can be a little bit challenging to grasp. So bear with me and try to pay attention. Why we have rows, okay? Why do we have the rows, and why is hydrogen and lithium and sodium and potassium, why are they the first member of each row, okay? So let's talk about that a little bit. Okay, so what you need to realize is that, do you remember what I said about electrons? Electrons exist in 3-dimensional spaces around the atomic nucleus, and only 2 electrons can exist in any one 3-dimensional space. Okay, you have to remember that. You might want to write that down. And then do you remember what those 3-dimensional spaces are called? They are called orbitals. So a 3-dimensional space that houses electrons is called an orbital. Okay, think about that. You may want to write that down. And how many electrons can exist in any one 3-dimensional space, in any one orbital? How many electrons did I say a little earlier can be in one orbital, one 3-dimensional space? 2. 2 electrons can be in one 3-dimensional space. But do you only have 2 electrons total? No, look at this. Hydrogen has 1 electron, helium has 2, but look, lithium has 3. So if only 2 electrons can live in one 3-dimensional space, what happens if you're like lithium and you have 3 electrons? Where does the third one go? Well, what that means is lithium must have 2 orbitals, right? Does that make sense? With 2 electrons in the first orbital, and then another electron in a different orbital, a different 3-dimensional shape. Do you realize what that means? Are you following along here? If you have a bunch of electrons, that means 2 electrons are in the first 3-dimensional shape, first orbital, and then you'll have a different orbital with a different shape, and then that can house 2 electrons, and then you'll have another orbital with another shape. And what are the orbitals? They're just 3-dimensional spaces. They're 3-dimensional shapes. They're the football field. They're the Cowboy Stadium, right? Okay, and then so think about Cowboy Stadium. Like if this group of seats that looks like a circle, if that's a 3-dimensional space that you could sit in, 2 people could sit in this zone, right? Or in these seats. And then 2 people can sit in these seats, and then 2 people can sit in those seats, and all the seats together make up the Cowboy Stadium. I don't know if that makes any sense, but I'll explain it more as we go. So here's what we're doing. Okay, let me bust out my little whiteboard here and try to break it down, because this can be a little bit tricky to understand, but try to bear with me. So again, what did I say the atomic nucleus looks like? a little pencil eraser, tiny pencil eraser, tiny nothing in the middle, somewhere near the middle of the atom, you've got this tiny little nub, right, of mass. Now, what if you have a bunch of electrons? Where are the electrons hanging out? Well, the electrons hang out in three-dimensional areas. So look, here's the first three-dimensional area, okay? Look, I'm drawing a circle, you see? A dashed line circle. This is called an orbital. It's a three-dimensional space around the atomic nucleus. And how many electrons can be in that one space, that one three-dimensional space that I just drew? Do you remember how many electrons can be in one orbital? 2. So here's an electron buzzing around. Here's an electron buzzing around. And by the way, even though it's called an orbital, the electrons aren't going around in a circle like the Earth orbiting the sun, okay? That's not how it works. The electrons can be anywhere, like a cloud, right? The electrons can be anywhere in this orbital, and they can even briefly leave the orbital and come back. So the electrons are in this three-dimensional space, anywhere in that space most of the time, okay? But what if I'm lithium? What if I have another electron? Can it exist in this same little space, the same little cloud, the same little three-dimensional space as these two? No, right? Remember, each little three-dimensional space, each little orbital, it's called, can only house 2 electrons. So now I need to have a different three-dimensional space. Look at this. I'm actually starting a whole new layer of space. This is another orbital. It's a bigger circle. So now if I'm lithium, my third electron lives in this new space. Okay? And how many electrons can be in that new space? Up to 2. So if I'm beryllium, my electrons, I have 4 total electrons. 2 of them are in the first orbital. The other 2 are in the next orbital. Okay? And then if I have even more electrons, I'm going to have, look, another three-dimensional shape. This one actually looks like a figure 8, right? It's like a p orbital. It's called the p orbital, but you don't need to know that. Okay? And if I have, and that can house 2 more electrons, okay? And then if I have even more electrons, I'll have another figure 8, right? Another three-dimensional shape, which can house another 2 electrons. And if I have even more electrons, I'll have another three-dimensional shape, and it'll have another 2 electrons. So you see that? That's a bunch of electrons I can have. And every time I have 2 more electrons, I'm going to have a new three-dimensional shape. And now look, it's really crowded with electrons, isn't it? It's really crowded up with electrons. I've utilized all this space. So if I have even more electrons, look what I'm doing again. I'm going to a whole nother layer. You see? These layers, every time you go out to the next layer, the layers have a name. That's called a shell. Okay? The layers are called shells. So I can have 2 electrons in the next shell, this orbital in the next shell, and then I can have another bigger dumbbell-shaped orbital in there. So here's the thing you need to understand. I know it's a bit confusing. Okay? Here's what you need to understand. Electrons exist in three-dimensional spaces, three-dimensional areas called orbitals. 2 electrons can exist in any one orbital. But some atoms, you know, the ones that have a lot of electrons, they're going to have a lot of orbitals, right? Okay? So look at this here. Look at this here. Hydrogen, right? Hydrogen. How many electrons does it have? Here, let's go through this together real quick, because I know it's challenging. Let me get my whiteboard out. Hydrogen has 1 proton. So how many electrons does it have? It has 1. So look, if this is the atomic nucleus, let's look at the first orbital. Hydrogen has how many electrons? 1. There you go. That 1 electron is in that 1 orbital. So how many orbitals does hydrogen need? Just 1, right? And there you go. There it's its electron in that 1 orbital. Okay. And by the way, you see this circle I drew? That's called the first layer of orbitals, the first shell of orbitals. Okay. What about helium? Helium. How many protons did it have? 2. So how many electrons does it have? 2. There you go. So where does its electron live? In that same orbital. So helium has 2 electrons in that orbital. Okay. There you go. That's all there is to helium. So look at the periodic table of elements real quick. Hydrogen has 1 electron in the orbital. Helium has 2 electrons in that first orbital. So why do we go to the next row with lithium? With lithium, why do we go to the next row? Well, here's why. You need to write this down. Because now we bump ourselves up to the next shell. We've gone from the first shell of orbitals to the second shell of orbitals. So check this out. Lithium has 3 electrons. Can the third electron be in the same orbital? No. Now you have to bump it up and go outwards to the next shell. And look, here is an orbital in shell 2. Well, you know what shell means? Think about shells as layers, right? You have layers of orbitals. The layers are called shells. And do you know what? You can have more than 1 orbital in each shell. This is what you need to understand. You can have more than 1 orbital in each shell. So how many orbitals do you think are in shell 1? Remember I said in shell 1 you have this orbital. It's actually called the 1s orbital, but you don't really need to know that. It has 1, 2 electrons in that orbital. So what can you say? This is called shell 1. How many orbitals in shell 1? In layer 1 has 1 orbital. Okay, shell 1 has 1 orbital. How many electrons in each orbital? 2. So lithium, who has 3 electrons, what do you have to do? Again, the third electron can't exist in this same orbital. So with lithium, you go to the next shell. Look, you're actually going to the next layer. You see how I went outwards? That's the next layer. That's called shell 2. But here's the thing you need to understand about shell 2. Layer 2. Layer 2 is not just one little 3-dimensional space, one little orbital. It's actually 4 orbitals. Okay, this is really important to understand. Shell 1 has 1 orbital. So how many electrons can it house? 2 electrons. Shell 2 has 4 orbitals. So how many electrons can it house? Well, 4 times 2 is 8. So there could be 8 electrons in shell 2. And I'll explain this. So look. So lithium has, this is another orbital in shell 2. Lithium would have its electron floating around like that. And then beryllium, which has 4 electrons, there you go. It would also be in that orbital. But what about carbon? Carbon has even another electron. What do we do now? Well, here's what you need to understand. With carbon, it's going to have yet another. Oh, I'm sorry. This is beryllium. Boron. Let's do boron. Boron has 5 protons and 5 electrons. Where's the 5th electron going to go for boron? Here's the thing. Look at this. Look at this. Here's another 3-dimensional shape. It's called an orbital. You see that? Here's another 3-dimensional shape which can house up to 2 electrons, but you're not bumping yourself up to the next shell. It's not like you're going outwards into another layer. You're staying in the second layer, the second shell, but now you've got multiple orbitals in the second shell. So boron has an electron here. Carbon would have another electron in that same orbital. And then what if I'm nitrogen? Well, there's another another three-dimensional space there. And if I'm oxygen, there's another one there. And if I'm fluorine, and if I'm neon, neon has another one there. Now look, by the time you've gotten to neon, which has 10 electrons, you've filled the outermost shell, which has how many orbitals? 4 orbitals, which can house 8 electrons. And now guess what? If you go to sodium, which is on the third row of the periodic table of elements, now you're going to the next shell. You see that? You go into shell 3. Shell 3. So when you go from neon to sodium, you start shell 3. And shell 3 also has 4 orbitals. So how many electrons can exist in shell 3? Another 8. Okay, so hopefully that makes sense. Let me show you what I've been talking about real quick again. This is the first shell. The first shell has how many orbitals? 1. You see, this is the first shell called the 1s orbital. It can house how many electrons? 2. Then you have to bump it up to the second shell. Okay, the second shell has how many orbitals? 1, 2. Remember the figure 8 style I told you about? Called p orbitals. And then 3. And then 4. So the second shell of electrons has how many orbitals? 4. Okay? And so how many electrons can exist in the second shell? 8. All right? How many electrons can exist in the first shell? 2. How many electrons can exist in the second shell? 8. And then if you go to the third shell, there's another 4 orbitals. How many electrons can exist in the third shell? Another 8 electrons in the third shell. So did you follow that? 2 electrons exist in the first shell because there's only 1 orbital in the first shell. Then you go to the next shell. 8 electrons can be in the second shell because it has 4 more orbitals. And then you go to the third shell. Another 8 electrons can be in the third shell because you have another 4 orbitals in the third shell, and so on and so forth. So what does that have to do with the periodic table of elements? Look, well, here you go. Look at the first row of the periodic table of elements. How many orbitals in the first layer of, in the first shell, I should say? How many orbitals? 1. How many electrons can exist? 1, 2. 2 electrons exist in the first shell, and then you have to start a new shell. You see, lithium starts a new shell. And then how many electrons can exist in that second shell? 8. So look, 1, 2, 3, 4, 5, 6, 7, 8. Neon has filled the second shell. And then you've got to start a third shell with sodium. And how many electrons can exist in the third shell? 1, 2, 3, 4, 5, 6, 7, 8. So argon has filled the third shell. Do you notice what's happening? This final column of the periodic table, these are all of the elements that have filled the outermost shell, filled the shell. And the first column is what? Hydrogen, lithium, sodium, potassium. These are the elements that only have started a new shell, right? These are the ones that have 1 electron in the outermost shell, right? Again, these are called the noble gases on the right. In column 8, these are called the noble gases. They have filled their shells. In the first row, you have all of the elements that only have 1 element. 1 electron in the outermost shell. These have 1 electron in the outermost shell. What about these column 2? What about column 2? Column 2 has 2 electrons in the outermost shell. Column 3. Hold on. Let me show you what I'm talking about. Column 1. 1 electron in the outermost shell. See this little dot? That little dot represents the outermost shell of electron. That little dot represents the electron, and this ring represents the shell, right? You see? Hydrogen has 1 shell, 1 dot, so it has 1 electron in its outermost shell. Lithium has 2 rings with 1 dot on the outer ring, so lithium has 1 electron in the outermost shell. Sodium has 1 electron in the outermost shell. What about beryllium and magnesium? They have 2 electrons in their outermost shell. Boron has 3 electrons. Aluminum has 3 electrons in its outermost shell. So you see what the rows represent? The rows represent the shell you're talking about. So the first shell has 2 electrons. The second shell has another 8. The third shell has another 8. So what are the columns? What are the columns? The columns represent the number of electrons in the outermost shell. So how many outermost shell electrons does hydrogen have? 1. How many outermost electrons does lithium have? 1. How many outermost electrons, outer shell electrons does sodium have? 1. So you see, the first column, these all have 1 electron in their outermost shell. The second column, these all have 2 electrons in their outermost shell. The third column, 3 electrons in the outermost shell. And so on and so forth until you get to the last column. What do they have in common? They have filled their outermost shell. They have filled their outermost shell. So some people might be wondering, why is helium way over here at the top right? Why isn't helium here in this spot here above beryllium? Because doesn't helium have 2 electrons in its outermost shell? How come it's not here? How come it's way bumped over here? Well, hasn't helium filled its outermost shell? How many electrons could be in its shell? 2. So helium has filled its outermost shell, and it's more important than that it comes over here in the final column to exhibit to show you that it has a filled outermost shell. Okay, that's why helium is bumped all the way over here, and it's not presented here with all the other elements that have 2 outermost shell electrons. Now, here's something important that you need to understand about the periodic table of elements. I keep talking about outer shell of electrons, outer shell of electrons. And instead of me saying outer shell of electrons a million times, because that gets tiring, what we say instead is valence shell. Okay, so you should know that term, valence shell. Valence shell means outermost shell. What is the valence shell of the first row? The first shell. What's the valence shell here? The second shell. What's the valence shell here on the third shell? Third shell. Now here's where it gets a little tricky. Something like hydrogen. How many electrons does it have total? 1. How many valence electrons does it have? 1. But what about carbon? Look at carbon. Look at carbon. How many total electrons does it have? 6, right? Because you have 2 electrons in the first shell, and then you have 4 electrons. See the 4 dots? 4 electrons in the second shell. So if I were to ask you how many total electrons does carbon have, that's a different question than how many valence electrons does carbon have. Does that make sense? Carbon has 6 total electrons, 2 of which are in the first shell, but it has 4 valence electrons because valence means outermost shell. It only has 4 electrons in the outermost shell. 2 of the electrons are inner on the first shell. Okay, so again, what does the final column represent? Helium, neon, argon. These are called the noble gases, and they're called noble gases because they have a full outermost shell of electrons. Okay, the first column, they have 1 valence electron. The second column, they have 2 valence electrons. Third column, they have 3 valence electrons. Fourth column, they have 4 valence electrons. Okay, that's how the periodic table works. And now you understand the rows tell you what shell you're talking about. Shell 1, shell 2, shell 3. And the columns tell you how many valence electrons you have. Okay, valence electrons you have. So that's how the periodic table works. Okay, so Now we can read the periodic table of elements. And here's something else that's very interesting and very important to understand about chemicals and the periodic table of elements. Okay, you ready for this? This is very important to understand. And after this point, I'll take another break, and you can take a break as well. Uh, and that is this. Look, have you did you notice that all of these have the full valence shell of electron? These are called the noble gases, and then these guys have almost full valence shell. They have seven electrons in their shell. They just need one more. And do you notice that? Well, that's actually really important to understand. I'll explain why. Okay. Um, here's the thing. Here's the thing. The noble gases at the right, these are called noble gases because these elements do not chemically react. Okay, when helium meets helium, there's no chemical reaction that happens. When neon meets another element, there's no chemical reaction. Argon, none of these noble gases do chemical reactions. And the reason they don't chemically react is because of the simple fact that they have filled their outermost shell. They have filled their valence shell with electrons. Okay, so these these elements have filled have they're just naturally they naturally I should say naturally have a full valence shell of electrons, and because of that, they do not participate in chemistry. They do not make bonds. They do not make molecules. They do not do any interesting things and explode. They just exist. Okay? But what about the rest of these guys? What about the rest of these guys? Column 1, column 2, column 3, column 4, column 5, column 6, column 7. What about these guys? We're just focusing on the first 3 shells of the periodic table, by the way. We're not talking about the rest of them. But what about the rest of these guys? Do they have full valence shells as well? No. And that is the problem. Here's the thing. You've heard of chemistry. This chemical reacts with that chemical, and then those chemicals react, and there's chemical reactions, and bonds form, and molecules form, and then molecules break down. You've heard of chemistry, right? Where all of these things are happening. Why do all of those things happen? Well, because the reason chemistry happens, okay? The reason chemistry happens is because all of these elements would like to fill their outermost shell, okay? And can they naturally have a full outermost shell like the noble gases? No, they can't naturally do it. So they have to do it by bartering, trading, sharing, stealing electrons. Okay. So for example, fluorine and chlorine in the column 7, you see fluorine and chlorine. They both need just one more electron. Just one more electron. So they're going to try to steal one electron so that they can fill their outermost shell and trick themselves into feeling like the noble gases, right? What about the first shell of elements? What about the first shell of elements? They just have one pesky electron in their outermost shell. Do you think it's easy for these guys? Do you think it's easy for column 1 to gain 7 more to be a noble gas state? No. So what do you think these guys do to try to fill their outermost shell? Well, how about give away their electron? Look at lithium. What if it gave away this one electron? Now it's lost its outermost shell of electrons, and it's gone to its inner shell of electrons, but it's full, so it's happy. You see that? Sodium as well. Sodium has 1 electron in its third shell. What if it gave away that 1 electron? Now it bumps down to it drops down, I should say, to the second shell, and that second shell is full, so it's happy. You see that? It has a full outermost shell. So all of these atoms want to feel like the noble gases, and they're not naturally like that. So these guys here in the seventh column, they're going to try to get an electron. These guys here in the first column, they're going to try to give away an electron. So what do you think happens when column 1 meets column 7? Well, there's going to be a chemical reaction where, for example, lithium will give chlorine an electron. It'll be lithium chloride. Have you heard of lithium chloride? It's a type of salt. Anyway, what about the rest of these? oxygen will try to bind with something, nitrogen will try to do something. They're all going to try to barter, trade, steal, share, and they're all going to try to react with one another. That's what a chemical reaction is. That's how molecules form and ions form, because the rest of these elements want to fill their outermost shell. And have you noticed this? Look, fluorine and chlorine are probably going to do the same kind of stuff because they just need one more electron. Hydrogen, lithium, and sodium, they just need to give away one. Nitrogen, it has 1, 2, 3, 4, 5 valence electrons, and so does phosphorus. Do you see that? Do you see what I'm saying? So, do you see where I'm getting? This is the main point. The columns are important to understand because these are elements that behave in a similar fashion. Column 1, these guys behave in a similar fashion chemically. Column 2, these chemicals behave in a similar fashion chemically. Column 3, these behave in a similar fashion chemically. So when you look at the columns, because they have the same number of valence electrons, when they undergo chemical reactions, they're going to behave in a similar way. Isn't that interesting to understand? And that's why the noble gases all behave the same way as well. Okay, one last thing. So what determines the chemical properties of an element? What determines the chemical properties and how that chemical reacts in an element? Its number of valence electrons. If it has a full valence electron shell, then it doesn't react. It's a noble gas. If it only has one valence electron, it's going to try to give away the valence electron. If it has 7 valence electrons, it's going to behave the same way. It's going to try to find an electron. So the reason chemistry happens is because of the valence shell. Okay, and different elements with the same number of valence electrons are going to behave chemically in the same way. Okay, and that makes sense. So think about it. Remember what I said an atom is? An atom's basically like a football, like a Cowboy Stadium size thing of empty space, right? And imagine if one atom meets another atom, right? One atom meets another atom. What's the thing that talks? What subatomic particle talks between the two atoms? What's talking? Is it the atomic nuclei that are meeting each other and negotiating stuff? No, the atomic nuclei are really far apart. So when two atoms come together, their empty spaces, their Cowboy Stadiums come together. What's actually communicating between the two atoms? The outermost shell of electrons, right? Does that make sense? So you can see now why the valence shell is so important, because when two atoms come together, it's the valence electrons that see one another. And that is what causes a chemical reaction to happen. And that is what chemistry is, okay? So now you understand the periodic table of elements, you understand subatomic particles, you understand what happens when chemicals meet one another and why they chemically react or why they wouldn't want to chemically react, and why some elements chemically react the same way, why some elements chemically react in different ways, what are electron shells, what are electron orbitals. So hopefully you understand that, because that is the basis of chemistry. If you understand what I just said up till this point, you understand the concept of chemistry, okay? Anything from here is just icing, right? Icing on the cake. So I'm going to take a little break again. Oh, I need to grab some coffee or something. Another little break time. We'll come back and we'll talk a little bit more about chemistry. All right, everyone, welcome back from break time. Let's take a look what we learned so far. We learned about the periodic table of elements, and I told you that the over here, the noble gases do not chemically react because they have a full valence shell. Now, look at the rest of these elements. They do not have a full valence shell, and that's why chemistry happens, because they have to try to fill their valence shell. Just remember that. I should say elements. Elements want to have a full valence shell. The noble gases already have a full valence shell, so they don't need to do any chemistry. They do not need to participate in chemical reactions. However, the rest of these elements are trying to fill their valence shell. Just remember that as we go along. Remember, the first shell has one orbital, the second shell has four orbitals, the third shell has a further four orbitals, and so those are the only shells we're going to be discussing in this class. Why? Because biology is made up of elements. Your cells in your body are made up of elements, and those elements are the majority of them are on the first three rows of the periodic table. All right, let's keep going. So, if you are not lucky enough to be a valence electron, if you are not lucky enough to be an element with full valence shell, like a noble gas, then you need to, like I said, undergo chemical reactions. And when this happens, usually you form chemical bonds. These interactions usually results in atoms staying close together. This is from atoms with incomplete valence shells can share or transfer valence electrons with certain other atoms. Did you see that? If you don't have a full valence shell, you will share or transfer valence electrons with certain other atoms. This results in what's known as chemical bonds, which hold the atoms together as molecules. Okay, so actually let me show you an example on my board here before we start. Take a look. It's going to wipe off my board. I want to show you an example of a chemical reaction. Okay, very simple, the simplest chemical reaction I can think of, which is hydrogen. Okay, so look, here's hydrogen. How many valence electrons does hydrogen have? Do you remember? It has one valence electron. Does it have a full valence shell? No, remember, it could have two electrons in that shell. The first shell has one orbital, and so the first shell can house two electrons. So is hydrogen a noble gas? Is hydrogen happy, quote unquote happy? No, hydrogen kind of wishes it was more like helium. Hydrogen wishes it had two electrons so it could fill its outermost shell, its valence shell. It wishes it could fill it by having one more electron. So hydrogen's looking for a way of getting that other electron, either by sharing or stealing or giving, who knows. So let's look at what happens when hydrogen meets another hydrogen. Okay, look, this hydrogen has one valence electron, this hydrogen has one valence electron, and neither of the hydrogens are happy, but what happens if they come into contact with one another? Well, they kind of say, hey, you have one, I have one. Why don't we share? So they share these valence electrons. I'm going to draw it like this. It's called Lewis dot structure. And look, now this hydrogen is happy, quote unquote happy. Why? Because it feels like helium. It feels like it's filled its outermost shell. Look, this hydrogen has two electrons. This hydrogen thinks it has two electrons. It's kind of like when you're hanging out with your brother and you have a car and your brother has a car and you decide to share cars, whatever car's available. Well, then what do you tell all your friends, right? You tell all your friends you have two cars, even though do you technically have two cars? And he's telling all his friends he has two cars too, but does he technically have two cars? No, but you feel like you do because you have access to two cars. So this hydrogen feels it has access to two electrons. This hydrogen feels like it has access to two electrons. So even though they're sharing, they each feel as though they have two. So they feel as close to the noble state, as close to the full valence electron state as possible. So they're both satisfied. Did you see that? So this here is called H2. Its molecular formula is H2, and that's called hydrogen gas. So if you ever release hydrogen into the atmosphere, it doesn't hang out as H. it quickly bonds with other hydrogens. For example, it'll form H2. And the reason for that is because it's trying to fill its outermost shell. Did it do it by stealing electrons or donating electrons? No. In this case, it did it by sharing electrons. Sharing electrons. And sharing electrons like this is called, let's go back to the slides, a covalent bond. Notice what happened here. Take a look. Here's hydrogen. It met another hydrogen. They came together and shared those electrons to form the hydrogen molecule. Molecule means atoms, which are now bound together with these chemical bonds. This is H2. And what is that bond called? When you're sharing electrons, it's called a covalent bond. When you're sharing electrons, it's called a covalent bond. So look at this again. This hydrogen is sharing with that hydrogen. They're sharing, and that's called a covalent bond. When you're sharing, it's a covalent bond. Let me show you another covalent bond. Let's look at oxygen real quick. Let's hop back to the periodic table of elements real quick. Let me show you what I'm talking about. Look at oxygen here, right? You see oxygen. It's in the second row of elements, so it's in the second shell. Do you remember how many orbitals are in the second shell that we discussed? There are 4 orbitals in the second shell. So how many electrons can be in the second shell? Well, 4 times 2, because remember there's 2 electrons in every orbital. There could be 8, right? So lithium has 1 valence electron. Beryllium has 2 valence electrons. Boron has 3 valence electrons. Carbon has 4. Nitrogen has 5. Oxygen has 1, 2, 3, 4, 5, 6. Oxygen has 6 valence electrons. How many total electrons? 8, right? Because it has 2 non-valence electrons. But anyway, it has 1, 2, 3, 4, 5, 6 valence electrons. Does it have a full valence shell? Is it full like neon is? No. How many more valence electrons does oxygen need to be full? It has 6 valence electrons. It needs 7, 8. It needs 2 more, 1 here and 1 here, right? Oxygen needs 2 more electrons to have a full valence shell. So, do you think oxygen hanging out by itself is very happy? Quote unquote happy? No. Let's go back to our board. Okay, check it out. Here's oxygen. There's oxygen. How many valence outermost shell of electrons? 1, 2, 3, 4, 5, 6. 6 valence electrons. How many valence electrons would it prefer to have to be full shell? 2 more, right? 8 valence electrons. So, what do you think happens if a hydrogen comes along with its 1 valence electron? Could they share? Sure, check it out. Hydrogen shares its electron with this electron from oxygen. Now they're sharing. Look. Is this hydrogen happy? Quote unquote happy? Yes, this hydrogen actually filled its outermost shell because its outermost shell is the first shell. The first shell only has 1 orbital. There you go. There's 2 electrons in that 1 orbital. Hydrogen's perfectly happy. But is oxygen happy? Does it have a full valence shell? No. It has 1, 2, 3, 4, 5, 6, 7. Now it's better off, but this is not preferable. So what happens? Another hydrogen comes along with another electron, see? And now this time, this hydrogen will share again with this oxygen's electron. And now this hydrogen is satisfied. It has 2 valence electrons. It has filled its outermost shell. And now is oxygen satisfied? Yes. Look, 1, 2, 3, 4, 5, 6, 7, 8. Now everything is satisfied. All of the players are satisfied. And this molecular formula is called H2O, which is water. So you see, now you understand why water forms when oxygen comes into contact with hydrogen. Oxygen gas with hydrogen gas, together they can form water. Okay, and this is why. Okay, so and what kind of bonds are these when you share? What kind of bonds? What's that called when you're sharing electrons to make a chemical bond? That's called a covalent bond, which is a very strong type of chemical bond. Very strong bond. Okay? So that's good to understand. Here's another example. Here's another example. Let's go over this one. Here's a regular old oxygen. How many valence electrons did oxygen have? 1, 2, 3, 4, 5, 6. Not very happy. Here's another oxygen with its 1, 2, 3, 4, 5, 6 valence electrons. Are either of these oxygens satisfied? No. But what if this oxygen shared its electron with this electron from this oxygen? Now each one thinks it has what? Each one thinks it has 1, 2, 3, 4, 5, 6, 7. Are they satisfied yet? Not yet. How about if this one shared this and this one shared that as well? Now, are they satisfied? Yes. Look. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Both of them are satisfied because each one is sharing 2 electrons. Does that make sense? That is actually called O2. And because that's oxygen gas, by the way. Because each of these is sharing 2 electrons, it's actually not just called a covalent bond. It is a covalent bond, but it's called a double covalent bond. You know why? Because each player is sharing 2 electrons. In hydrogen, if you remember hydrogen, each player was sharing 1 electron. So that's called a single covalent bond. Another way of drawing that is H line H. That's a single covalent bond. What would this be? These oxygens, it would be O, double bond to O. Double covalent bond. Double covalent bond. Single covalent bond. It all has to do with how many electrons is each player sharing, each element sharing. Okay, let me show you a triple covalent bond. You could have that as well. It's really interesting stuff. Let me show you a triple covalent bond. Okay, nitrogen. Nitrogen, if you look at the periodic table, take a look here actually. I have it pulled up. Let me show you. Nitrogen has 1, 2, 3, 4, 5. So you have 1, 2, 3, 4, 5 valence electrons. How many does it wish it had? 6, 7, 8. 3 more, right? 3 more valence electrons to be satisfied, to have a full valence shell. So let's take a look at that real quick. Nitrogen has 1, 2, 3, 4, 5 valence electrons. I'm just drawing the outermost shell of electrons. Is it happy? Happy? Nope. Here's another nitrogen with its 5 valence electrons. It's not happy either. But what if they start to share? Hey, I'll share this one if you share that one. Okay. Are they satisfied yet? Nope. 1, 2, 3, 4, 5, 6. Each one thinks it has 6 now. It's a little better than 5, but not quite there yet. How about if I share this one, you share that one? Are they happy yet? Nope. 1, 2, 3, 4, 5, 6, 7. Not quite yet. Close. What about if I share this one? You share that one? Now what? Oh yeah. 1, 2, 3, 4, 5, 6, 7, 8. Each one thinks it has 8 because each one is sharing 3. Does that make sense? So this is called N2, nitrogen gas. And this, another way of drawing this would be N triple bond N. Okay, so hopefully that makes sense. This is what covalent bond means. You're sharing electrons. So why would you want to share? Well, to fill your outermost shell, to fill your valence shell with electrons. You can accomplish that by sharing. Okay, so again, covalent bonds, you can have single, double, triple covalent bonds. You share electrons in order to fill your outermost shell with electrons. It's pretty neat stuff. All right, now what else? Here's another concept. Oh, by the way, here it is, what I was just drawing. Single bond, double bond, triple bond. Okay, let me show you another concept here. This is actually, I'm skipping a little bit ahead. And this is the concept of electronegativity. All right, let's talk about the concept of electronegativity. This is very important to understand, okay? Electronegativity. What does electronegativity mean? What you need to understand is that different atoms on the periodic table of elements have a different affinity. Affinity means attraction for different of their electrons. Different elements have different attraction or affinity for electrons. So take a look at the periodic table of elements here. Remember, you have the periodic table. Well, what you need to understand about the periodic table is that the elements at the bottom left, you see, starting with francium here at the bottom left of the periodic table, these elements are the least attracted to their electrons, their valence electrons, okay? These elements really, you could think of it like this. It's really easy to steal their electrons. They're not holding on to their electrons very tightly, okay? It's actually quite easy to take their electrons or hog their electrons or bully them for their electrons, right? Does that make sense? And electronegativity, which means greediness or affinity for electrons, electronegativity increases as you go right and as you go up on the periodic table of elements. So the greediest or the most electronegative elements are at the top right of the periodic table. So again, electronegativity increases to the right, and electronegativity increases as you go as you go up on the periodic table. So these are the most greedy elements on the periodic table for their electrons, okay, at the top right. Okay, why do you care? Why is that important? Well, it's important because it's going to result in all kinds of issues when chemical bonds are formed. The greedier you are, the more you're going to bully the ones who aren't greedy, okay? And that's just the way it works with chemical bonds. What you should realize, again, the least electronegative elements are at the bottom left. The most electronegative elements are at the top right. Another thing you need to realize, okay, please make a mental note of this or write it down. As you go from left to right, the jump in electronegativity is quite big, okay? As you go from left to right, each step has a huge jump in electronegativity, okay? But as you go from down to up, as you go north, as you go from bottom to top, each jump is incremental, okay? The jump is there, but it's not very big, okay? So when you go left to right, big jumps in greediness, down to up, tiny jumps in greediness, okay? Please remember that. Here's another thing you need to understand, okay? This is super important. Remember this, okay? Let me show you something. You see how hydrogen is over here? Whoops. You see how hydrogen is over here at the top left of the periodic table? Well, that's where it belongs on the periodic table. But if we're talking about electronegativity, hydrogen really doesn't belong here at the top left of the periodic table. Let me show you something. This is, again, very important. Let me go into, maybe I could draw a little bit on this. Okay, so let me show you something. If we're talking about hydrogen, don't think of it as over there. Okay, hydrogen, if you're talking about electronegativity, let me show you something. Hydrogen belongs here. Okay, hydrogen belongs here. Can I insert text here? Can I write something like, yes, I can. Look at that. So look, please remember this. If we're talking about electronegativity, hydrogen does not belong here. it belongs right here on top of carbon. Okay? Do you know why I say that? Well, because carbon and hydrogen have roughly the same electronegativity. Carbon and hydrogen have roughly the same electronegativity, the same greediness for electrons, the same affinity for electrons. Okay, so just remember that. Please remember that. That's actually very, very important. Carbon is not greedier for electrons than hydrogen. Why do you care? It's going to become very, very apparent very, very soon. Okay, let me take another quick little break. I'll come back and tell you why electronegativity is so important when we're talking about chemistry. All right, thanks again. I'll be right back. Take a quick break. All right, see you soon. Hey everyone, welcome back from the break. All right, let's wrap this part up. We were talking about electronegativity, and I was about to tell you why electronegativity is important when you're discussing molecular interactions. So let's just let's look at this again. Remember the final column here. Let me show you the final column. This is called these are called the noble gases, and they do not participate in chemistry. So let's ignore them. Let's ignore them when we're talking about electronegativity. So if we're ignoring the final column, what is the most electronegative atom? It would be fluorine, right? Fluorine is the most electronegative atom that participates in chemistry. And I guess over here, francium would be the least electronegative atom. Okay, so this column here, column 7, these columns, or this column here, these would be the most greedy atoms. These are the most greedy elements. Because remember I said greediness or electronegativity increases a lot when you go left to right, but it only increases incrementally down to up. So this column, these are the most greedy, the most electronegative elements. And that means that column 1, lithium, sodium, potassium, and so on, these are the least greedy elements. So what do you think happens when something like fluorine or chlorine, which is very, very greedy for electrons, what do you think happens when it meets lithium, sodium, or potassium, which is not greedy at all? If someone's very, very greedy and they meet someone who's not greedy at all, usually it ends up they take something, right? So that's exactly what happens. When column 1 meets column 7, that's exactly what happens. Column 1 gives its electron to the member of column 7. Let me show you what happens. Let me show you a very easy example. Look, sodium from column 1. See, Na means sodium. Sodium, which has 1 valence electron. Let's say it meets someone from the 7th column, chlorine, which has 7 valence electrons. It only needs 1 more to be happy. So let's take a look at what happens there. Here's sodium. Oops, I'm sorry. Here's sodium with its 1 valence electron. It's from column 1. Here's chlorine with its 7 valence electrons. What happens when the not electronegative sodium, or very low electronegative sodium, meets high electronegativity chlorine? Well, because chlorine is so electronegative, it can steal the electron from sodium. And that's what happens when column 1 meets column 7. Column 7, that member can steal the electron. And so is sodium called sodium atom anymore? No, because look, now because it's given up, it's donated its electron, it now has a positive charge, okay? And is chlorine an atom anymore? No, it has totally gained an electron. See that red dot? It has gained an electron. So it is now no longer an atom, it's an ion. So this is called sodium ion. That is called chlorine ion, or another way of saying that is chloride ion. Okay? And do you know what's going to happen? This is now positively charged. This is now negatively charged. What happens is they snap together, not because they're forming a covalent bond. This is not a covalent bond. A covalent bond is when you're sharing electrons. Are these guys sharing electrons? No, they're not sharing electrons. Look at this. Sodium is now positively charged. Chlorine's negatively charged. Sodium actually donated. They're not sharing. However, because they are oppositely charged, you know how opposites attract in chemistry, they will actually, almost like magnets attract, they will snap together. And that is not called a covalent bond, but it is a kind of chemical bond. It's called an ionic bond, okay? So an ionic bond is when ions of opposite charge, so a plus charge and a minus charge, snap together. That is called a ionic bond. And by the way, let me tell you this terminology real quick. You see this? Positive charged ion. Another word for positively charged ion is cation. And do you see this? Negatively charged ion. Another word for negatively charged ion is anion. Anion means negatively charged ion. The way I remember that is cats are a positive thing, so cation would be a positive charge. Okay? That's a pretty cheesy way of remembering it, but it's an effective way of remembering it. All right, one more thing I want to tell you, and that's this concept of oxidation and reduction. Okay, in biology and in chemistry, the terms oxidation and reduction are very, very important, and it has to do with what you just saw, the chemical reaction you just saw. If an atom loses an electron like sodium did, it becomes oxidized. That's what oxidized means. Oxidation is when you lose an electron. If an atom gains an electron, that's called reduction. Reduction means gain of electron, okay? So the way I remember this, by the way, let me tell you a quick way, easy way of remembering this on my whiteboard here. Okay, try to remember this. Loss of electron means oxidized. Gain of electron means reduced. So Leo, which sounds like lion, Leo says grr. Okay, that's another cheesy way of remembering something very important, and that is that loss of electron means oxidized, gain of electron means reduced. So if you remember that lions say grr, you'll remember Leo says grr, and you'll remember these terms, which are very, very important. So for example, in this cartoon animation, not animation, but this cartoon here from Facebook, this is an atom. It looks like the blue and the red spheres in the middle. That's the atomic nucleus with the protons and the neutrons. This looks like electrons, you know, the electrons. What's happening with this electron here? This electron that's fleeing in Braveheart fashion. Is this atom becoming oxidized or reduced? Remember, loss of electron means oxidized, gain of electron means reduced. This here, it looks like it's getting oxidized. This electron is leaving. Loss of electrons, that means oxidized. Okay. So what happened with sodium here? Sodium. Look, sodium lost an electron to chlorine, and chlorine became chloride. So sodium lost an electron, so sodium became oxidized to sodium cation. Did you guys follow that? Chlorine gained an electron. Chlorine became reduced to chloride anion. Okay, hopefully you followed all that. If not, just rewind and watch that again. Okay, so that's what an ionic bond is. And you see how that all has to do with electronegativity? See, column 7 was so greedy. Chlorine is so greedy for electrons. It just needs one more electron. So when it meets something like a sodium, it's going to just steal its electron. And sodium is now happy because look, because sodium gave away that one valence electron, it now effectively got rid of the whole shell. The whole third shell is gone, and now it does have a full outermost shell, but it's reduced down to its second. It's now down to only 2 shells, and the outermost shell is full. Okay, so they both effectively have full valence shells. All right, what else? Now, one last thing to talk about. Another way electronegativity works may have nothing to do with ionic bonds. It may have to do with covalent bonds. For example, oxygen, right? Oxygen might form water, right? Oxygen forms water by binding to 2 hydrogens, right? Okay, but look at this. Oxygen is to the right of hydrogen on the periodic table. Remember I said hydrogen should be right on top of where carbon is in terms of electronegativity? Well, let me show you something. Let me show you something real quick. This is actually the last point for this part 1 video, and then I'll make a chapter 2 part 2 video. Look at this. You've got oxygen. It has 1, 2, 3, 4, 5, 6 valence electrons. Remember that because it's in the second row of elements on the periodic table. All right, so what happens when hydrogen comes along? Remember, they share with covalent bonds, and another hydrogen comes along, they share with covalent bonds. That's water, isn't it? Remember, we talked about this before. But if you look at the periodic table of elements, remember here, look here, hydrogen, look, hydrogen is to the left of oxygen. So which one's greedier for electrons? Hydrogen or oxygen? Which one has higher electronegativity? Well, obviously, remember, electronegativity increases a lot when you go from left to right. So oxygen is actually much more electronegative than hydrogen. Oxygen is much more electronegative than hydrogen. So look at this real quick. This is actually really important, something you need to wrap your brain around. If oxygen and hydrogen are sharing these 2 electrons, that means that these 2 electrons they're not, by the way, this is really important to understand, these 2 electrons are not stuck right in the middle of hydrogen and oxygen. I just draw them that way. But these two electrons are free to go over here, they're free to go over here. They're being shared by the oxygen and the hydrogen. And these 2 electrons are being shared by this oxygen and this hydrogen. So they could be anywhere between the 2. Now, if you were sharing evenly, then these electrons would spend just as much time with this hydrogen as they do with this oxygen, right? If the sharing was done evenly, the electrons, which are negatively charged, would be spending just as much time with each partner, right? But which one's greedier? Which one has more electronegativity? That's right. Oxygen is the one with the higher electronegativity. Remember what electronegativity means? Attraction, affinity for electrons, right? So do you think the electrons are going to spend more time with the less greedy partner or the more greedy partner? The more greedy partner is going to be hogging the electrons. You realize what that means? The electrons, what that means is that they're still sharing, because this is a covalent bond, okay? But they're not sharing evenly. What does that mean? The electrons are going to spend more time with this oxygen and less time with this hydrogen. Does that make sense? If you're sharing with someone who's greedy, your car is going to spend more time with that greedy person than with yourself because you're less greedy for the car. So here's where you need to make a connection. Electrons are negatively charged, right? Negatively charged. If oxygen is spending a lot of time with these negatively charged electrons, what kind of partial charge, what kind of charge do you think oxygen is going to feel? The electrons are negatively charged. The oxygen is hogging the negative charge. Do I write negative charge like that? Negative charge? No, I don't just put that negative sign. You know why? Because did oxygen steal those electrons? No, oxygen didn't steal an electron. So you don't put a negative there, but it's hogging the electrons. So you put this. You see this symbol? That's delta, the smaller case d in the Greek alphabet. Delta means change or partial. So there's a partial negative charge. Does that make sense? The oxygen experiences a partial negative charge to it. You know why? Because it's hogging the electrons from this hydrogen and it's hogging the electrons from that hydrogen. And so what does the hydrogen feel? It's supposed to be sharing these electrons evenly too, but it's losing those electrons. Those electrons are spending way more time with the oxygen. So the hydrogens are going to experience a partially positive. You see, again, this isn't an S. I'm not drawing an S. That's D, the Greek letter D, small d for delta. Okay, so you see, what that results in are these poles, a slightly negative pole and slightly positive poles. You see that? This would be called not just covalent bonds, polar covalent bonds, okay? So have you ever heard that water is polar? You've heard water is polar. That's what it means. Water is polar because it has poles, a slightly negative pole, slightly positive pole. So the reason it has these slight poles, these slight charges, these poles, is because of uneven sharing of electrons. And so what you call that is not just a covalent bond, it's called a polar covalent bond, okay? When do polar covalent bonds form? When you have members of differing electronegativity, right? So oxygen has a higher electronegativity than hydrogen. So you're going to get a polar covalent bond, which means uneven sharing, which results in difference in partial charge, which results in a polar molecule. Okay, so that is why water is polar. It has everything to do with electronegativity, and hopefully now you understand, because that's super important to understand in biology, in chemistry, and also in physics. It's super important to understand this concept. Okay, now what if the sharing was between atoms of equal electronegativity? Anytime you're sharing with yourself, you're going to get equal electronegativity. So hydrogen, right, with its electron, it hangs out with another hydrogen, right, and they share these electrons. Is hydrogen greedier than hydrogen? Is hydrogen more electronegative than hydrogen? No, they have the same electronegativity because it's the same thing. So are we going to get a partial positive charge or a partial negative charge here? No, because the electrons are going to spend just as much time with each hydrogen, and that's not going to result in a polar covalent bond. This is called a non-polar covalent bond. And anytime you have two of the same, like O2 or H2 or N2, anytime you have two of the same thing bound to one another, you're going to have a non-polar covalent bond because you can't be greedier than yourself, right, for electrons. And one more thing you need to understand before I move on. One more thing. What if I have this molecule? Let's say I have carbon. How many valence electrons does carbon have? Take a look at this periodic table real quick. Look, carbon has, it's on the second row, has 1, 2, 3, 4 valence electrons. It's half full. It needs 1, 2, 3, 4 more electrons to be full. So let's look at this. Look, carbon has 4 valence electrons. It wished it had 8, right? So if a hydrogen comes along, it could share one. Another hydrogen, it could share one. Another hydrogen, it could share one. Another hydrogen, it could share one. This here, this is called CH4, also known as methane. Methane. Now, let's test your understanding. Is there polar covalent bonds that form here, or are these non-polar covalent bonds? Aha! Look at this. You remember? Here's where it comes around. You remember when I said hydrogen does not belong here on the periodic table of elements? If you're talking about electronegativity, it belongs here. Hydrogen belongs here, right on top of carbon. You know why? Remember why I said that? I said because carbon and hydrogen have roughly the same electronegativity. So look, if carbon and hydrogen are equally greedy or almost equally greedy for electrons, is there going to be a partial partial positive charge or partial negative charge anywhere? No. That's going to give you a non-polar molecule. Methane is a non-polar molecule because you don't have uneven sharing of electrons because carbon and hydrogen have the same electronegativity, so the covalent bonds that form between them are going to be non-polar covalent bonds. Okay? Very super important to understand. Why? Because it's not intuitive. And secondly, have you heard of fats and waxes and oils? Those things don't mix with water, do they? Do they? You know why? Because fats, waxes, oils, things like that, they're made of a bunch of carbons and hydrogens, and those molecules are going to be non-polar. And guess what? Non-polar molecules do not mix with polar molecules like water. So I'm going to make in part 2 of chapter 2, part 2 video, I'm going to explain why water and oil don't mix and why polar molecules and non-polar molecules don't mix. But in the meantime, that's where I want to leave you off. So think about that. Think about these concepts. This is chapter 2. We're just introducing chemistry. Hopefully it's a review for most of you. If not, please refresh your memory on this stuff or learn this stuff the best you can. Watch the video, read your book. Go to Science Corner on the second floor of Sabine Hall. There's tutors there. Come to office hours. Do what you need to do to grasp this material because this is the foundation of biology, biochemistry, chemistry, organic chemistry. And it's going to really help you out along the way. Okay, so just remember, you've got these covalent bonds. You can have polar, non-polar covalent bonds, and ionic bonds. So that's the main types of bonds we're going to talk about that are strong. All right. So thanks for watching. Tune in next time where I talk about part 2 to chapter 2. We're not quite done with chapter 2, but this is usually my first lecture. All right, about chapter 2. Thanks again for watching.